So we're now doing electric potential energy. This is 3.3. So again, please read Coletta, chapter 18. And this will be now associated with sapling homework number 6 in Physics 131 and sapling homework 5 in Physics 112. So chapter 18, homework 6, Physics 131, homework 5, Physics 1. So earlier in our in 3.0 and 3.1, we had talked about how voltage is associated with potential energy. Well, now we're going to talk about that. So what we learned from Physics 112 is that there is a work energy theorem. All right. So if you integrate a force with respect to distance, okay, in this case, our force is going to be the Coulomb force, which we learned back in chapter 1. The beginning of this is K Q1 Q2 over R squared. Well, now what we're going to do, I'm going to mark this up. I'm going to hit comments, move this back, and I'm going to use a pencil. All right, so suppose you had a charge Q1 that is in a field, is next to another charge Q2. Well, they're going to have a force on each other. And another interpretation of that is they're going to they're going to have a potential energy. They're going to repel each other. And so what you can say is that Q2 is creating a voltage that is going to work on Q1 to push it or pull it. Okay. So when we integrate the Coulomb force with respect to R, what we find is we get KQ1 Q2 over R. All right. Now, if Q2, we're gonna call Q1 the one charge that we're analyzing the energy on, and we're gonna say Q2 is going to be creating a potential energy that is going to be working on Q1. So we're going to pull Q1 in the front, which we did right here, and we're going to now highlight this, and this is KQ1 Q2 over R. Okay. Well, that is just a voltage due to the Q2 charge. And that voltage due to the Q2 charge is going to be working on the Q1 and creating an electric potential energy. All right? So the electric potential energy of two interacting charges, one interpretation is KQ1 Q2 over R. The same interpretation can be said is that it's actually just Q1 times the voltage caused by the other charge. All right. And the voltage of the other charge is this. So again, electric potential energy is U sub Q. So we're going to now designate electric potential energy as U sub Q due to a source charge. Well, that source charge is going to be working on a charge, and that is a voltage. So this is going to be the Q due to a source charge. And bringing this other Q up top here, we have QV. So the source charge is creating a voltage, and it's going to be working on our test charge Q, and that is going to be creating a potential energy. Okay, so I just brought it up there. So voltage is equal to joules per coulomb. So that means U is, again, since it's an energy, is going to be in terms of joules. V is in volts. And Q is in coulombs. All right. Well, there are two similarities. Again, U is a stored energy, or is called a potential energy. So in a gravitational field, we had learned in Physics 121, the potential energy due to gravity is going to be equal to mgh. And it can be said it's the energy of height. Okay? Well, U sub Q is going to be is also an energy of height, where voltage is actually like the GH. It's essentially the height. And that's what we learned in earlier in this chapter, that voltage is a height. Well, they have similar. They work in similar ways, right? So if you have a hill and you push a ball up a hill, you're going to be doing positive work in pushing it up the hill, and then the earth is going to be doing positive work in pushing it down the hill and converting it into kinetic energy. Well, that's the potential energy due to gravity. Well, we have another type of potential energy, and this is due to charge, right? So suppose you add a positive charge, and you're going to take another positive charge and bring it close to this, right? So you're going to have to push it with a force, right? Well, this other charge is creating voltages, okay? These are voltage lines, all right? And it's going to be fighting you as you push it up. So you're going to have to do positive work in pushing this positive charge closer to this source charge. All right. So you're going to be doing positive work in pushing our test charge Q sub 0 closer to this this source charge, which is creating a voltage. Okay. So they're two similar things. But we also know that charges not only push, but they pull. So obviously, if this is a negative charge right here, we're not going to be doing work. This negative charge is actually going to be doing work and pulling this charge towards it. So just remember that work, you've got the vector of the force. So if you're pushing if you are pushing an object in this direction, and that's the direction of your force, then you'll be doing positive work. Okay. So that is illustrated right here. Okay. So you're going to take a test charge. You're going to take a test charge and push it from A to B, point A to point B, and then also the same charge you can take it from point A to point C. You're going to be doing more work in pushing it in here because these charges are repelling you and they're going to be pushing against you. They're going to be pushing. So these test charges, these source charges are going to be doing, they're creating a force working against you, and you have to create a force in pushing them against these charges, right? And the same thing over here. So you're going to be doing positive work. You're going to be doing a work of 4 microjoules and pushing this test charge up to here. And then if you have to push it a further distance, well, even closer to these guys, then you're going to have to do even more work. Okay? So again, the electric potential energy is Q and a voltage. And it could also be the same Q times K of the source Q's over R. And these guys are the source Q's. And the test charge is what you're doing, is what you're moving. So these guys are the source charges. Causing the voltage. And this is the test charge that you're moving. So you're doing your energies, you're analyzing your energy on this guy right here. Well, these source charges, again, these source charges are creating an electric force working against your hand. You're pushing it to the right, which is now almost like a stored energy. It's almost like you're compressing a spring. Okay. So you are doing work in the direction of the force vector. And work, again, work is equal to negative delta U, right? And by the way, negative delta U, it'll be negative U final minus U initial, okay? And that's what delta U is, right? So you are doing work, so the direction of your force vector is the direction of the positive work. So you're doing positive work, and that in a weird way, these source charges are doing negative work when you're moving the test charge closer to them. Then when you let it go, these source charges then push the charge back out. They push the test charge back away, and so now they're doing positive work. Okay. So let's go ahead, and we had done a similar problem to this back when we were analyzing voltages, and I believe that was in the very first activity 3.0. Okay, so just real quick, we're going to recap what we had done in 3.0 is we wanted to find the voltages at A and D, and the voltages at C, and the voltages at B. So let's you want to do that, but also we're supposed to rank the strength of the electric field at A, B, C, and D from largest to smallest, and then we're also going to be drawing electric field lines around through B, through A, through C, and through D. And the electric field lines are perpendicular to these equipotential lines that are the green lines. So we're going to do this real quick to recap this, and then we're going to try this new one. And that's supposed to be charge. So let's go ahead and rank the voltages. Well, A and D, so in order to do that, we need to figure out what the voltages are. So we don't know A and D's voltage, but we can figure that out. So you have negative 200 volts and blank and negative 100 volts. So I'm guessing that this is going to be negative 150 volts here, and that the voltage difference is by 50 volts. So that's negative 150 volts. C is going to be then at negative 50 volts. B is going to be at negative 200 volts. A and D are going to be at positive 50 volts. So that means voltage at A equals voltage at D, which is greater to than the voltage at C. 50, they're both 50. They're greater than negative 50 volts. And negative 50 volts is greater than negative 200 volts. Oh. And B is negative 200 volts. All right. Again, to figure out the strength of the electric field, and strength of the electric field I'm interpreting as the magnitude of the electric field. Electric field is a vector, so positive and negative is based on the direction of the electric field vector. But I'm talking about the strength of the electric field. Well, where the voltage lines are close together is where you will find a stronger electric field. So B is in a dense part of where the voltage lines are close together. So we could see that that the electric field at B, the magnitude of that, is greater than everything else. And I think last time I thought that C might be just as dense as D. It's really too close to tell for me, so I'm just going to call them equal. D might be a little bit more dense than C, but not by much. And then the electric field at A is the weakest. All right. Let's draw the electric field lines. Electric field lines will go from high voltage to low voltage. We're probably having a lot of negatives over here. there's probably a positive right there, and there's probably a bunch of positives right here, because this is 100 volts, positive 150 volts, and this is 200 volts right here, and this is only 100 volts. So most likely there's only a 1 or 2 charges there. Anyways, so the voltage, so the electric field lines going through B are going to be perpendicular to the voltage lines. So the electric field lines and voltage lines are perpendicular, and that means it's got to be perpendicular at each one of these points, or each one of these intersections. And it looks there, and it's going to be going from positive to negative. Okay. Here is a perpendicular, 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 and so on and so forth. So it's looking like A is going to go and kind of go off in this direction. So that's the electric field lines due to A, and it then curves towards this. C is right here, and it looks like it curves this way. And D is looking like it's doing that, or maybe not so drastic here. A little bit more around it. Anyways, so we drew those electric field lines, and obviously electric field lines would be, a bunch of them would be over here, and they'd get less dense the further out we got, and then they get a little bit more dense as we get close to C again. So one of the questions that we're asking is, suppose a positive or negative charge is released at each location A, B, C, and D. Draw its path. Well, the electric field is going to be creating a force in its direction. So if we had a positive charge, the electric field, so I'm going to change the color, and I'm going to suppose I'm going to put a positive charge right here. And what I remember is that the electric field is kind of like the stream. If voltage is the altitude, then the electric field is the river. Okay, it's the stream that gets, is the river. So if we have a positive charge right here at B, it's not going to go towards these positives here. It's going to go towards these negatives. So the electric field is going to push this positive charge in the direction parallel to the electric field. So this guy is going to feel a force pushing it downstream. Okay. So the path of the electric field, so the electric field is the path that this positive charge would be moving. It'd be moving to the right, and it'd be moving in this direction. If we have a negative charge, and I associate blue and negative, whoops, I'm going to undo that. So I'm now going to draw a negative charge right here. We have a negative charge right there. Well, again, a similar situation, actually opposite, is you have electrons over here and you have a proton over here. Well, the electron is going to move opposite the direction of the electric field, and it's going to move upstream towards the higher potential. Or what I mean is towards the higher voltage where all the positives are located. So that means the electron is going to move, upstream and try to get here. Okay, so I'm trying to use this to illustrate the direction of the path of charges. And the path of the charges actually would be along the electric field path, because the electric field is creating a force, and that is going to be causing it to have a work done on it. And so if you know the path of the electric field, you know the direction of the electric field, that would be the path of a positive charge. opposite that direction would be the path of a negative charge. All right? So what we're going to do is do another situation similar to what we just did, and just say, suppose you put a positive charge at A, at B, at C, at D, and at E, and F, and just kind of go, which direction do you think this positive charge and this negative charge is going to move? Okay. So go ahead and draw its path. So let's change this color back to red, and we're going to represent a positive charge. Okay. Anyways, let's go ahead and do it. So suppose we put a positive charge right here. Which direction is it going to go? Is it going to move towards the other positive charge, or is it going to move towards the negative charge? What do you guys think? Well, the last activity, it's moving in the direction of the electric field. So what we can do as a quick hack is actually just draw the electric field. And the electric field would, interesting enough, it actually would flow along those lines. And it would be flowing from positive to negative. And so a positive charge is going to follow the electric field. Again, interpret the electric field as the stream, which is carrying a tennis ball that you threw into it downstream. So a positive is kind of like a tennis ball that you've thrown into the stream, and it's now going to be moving down at A, down at C, down in the direction of D, and stop right here. Okay, so we've actually just mapped A, B, C, not B, whoops. A, C, D, and that's it. A, C, and D. Suppose you put a positive charge right here next to this negative at point E. What would you find out? Well, it would go directly towards the negative. Remember, the electric field would be pointed towards the negative, away from the positive. So this electric field would be pointed directly towards it, and it would just go in that direction. So that's path E. Suppose we place a positive charge right here. Well, the electric field would be going in this direction, so that means the positive charge at B would be pushed to the right. And then probably out of the picture this way. All right. What about at F? Well, here's a positive charge. It's going to be pushing it in this direction, in the same direction as the electric field, which is going to be kind of off-screen down to the right. Well, we've done all of those, so let's do all of this again, but let's do it for a negative charge placed at each one of those locations. Okay? So I'm going to take all these back, and now let's place a negative charge at each one of those locations. So we already did the positive charge, and let's do the negative charge. All right? So I'm going to change this to blue, and we're going to go through and do what direction an electron would move. Well, an electron will move opposite the direction of the electric field. So here at A, the electric field would be pointed down and to the left, would be pointing in this direction. So that means the electron is going to go towards the positive. So that means the electric field is going to push it up towards this positive. At C, the electron is going to be moving towards A, And at D, the electron is going to be moving towards C. So basically opposite the direction of the electric field. Okay? Well, if we put an electron here at E, well, you have another electron right there. It's going to be pushing it away from it, okay, towards the higher potentials, okay, which is 0 in this case. So it's going to be going, it's at the potential, at the voltage of -20. It's going to then try to go to 0 volts, which is greater than -20 volts. How about B? Well, B, the electron is going to try to get towards that source. So it's going to try to go to the higher voltages away from the lower voltages. And F, the same type of thing, it's going to go directly to opposite the direction of the electric field. And so it's going to head up and to the left. Okay? So those are all the paths. All right. Let's keep moving on. So here is a conceptual problem. And U is, so we could interpret that the electric potential energy, and I'm going to use black, the electric potential energy is actually equal to a test charge plus the change in its voltage. And so that's why in 3.1 we practice what delta V is, and quantifying delta V. So this is the electric potential energy. Excuse me, the hiccups. This is the electric potential and electric potential energy. So it's U sub Q, and this is a test charge. We're going to put a positive Q here, and then we're going to put a positive Q here. Suppose you move a positive Q here, and then you move it directly to point F. Now, what I want to point out is that this distance here is equal to this distance here, right? And voltage is equal to KQ over D. Or R, rather. KQ over R, right? And so this positive Q right here is causing a voltage at I and also a voltage at point F, a distance R away in both those cases. So this positive Q is referring to this voltage source, right? So the voltage at F right here is KQ over R, and the voltage at I is also KQ over R. So in this case, the voltage final is equal to the voltage initial, which means that V final minus V initial is 0 volts difference. And what does that say? Well, that means that this positive charge, moving a positive charge from point I to point F, you will do no work in doing that. You will expend no energy. So that means the change in voltage is 0, so V final is equal to V initial. That means the delta U is 0, and work done is equal to negative delta U, and if delta U is 0, then negative 0 is 0. And so that's what you're supposed to do in these conceptual problems. So think about the voltage, think about the distances, and interpret voltage to those points. And then you're going to be putting a positive charge times that delta V and a negative charge times that delta V. All right? Let's try another one. Here are two different problems. Okay, so we're going to do the problem on the left. Again, you're going to be following this. So you're going to take a positive charge and you're going to place it at I, and you have a positive charge and you're going to place it at F. And again, let's say that this is that I is a distance D away, and that F is a distance 2 Ds away. All right. So point I and point F are, point F is 2Ds away. So that means the voltage at F is equal to this positive charge. So that's KQ divided by 2D. And the voltage at I is equal to KQ over 1D. So the voltage at I is greater than the voltage at F. Okay. And what does that mean? Well, if VI is greater than the voltage at F, then delta V here is going to be negative for this case. And if delta V is negative times a positive Q, so that'll be a positive, the positive Q times a negative delta V. That'll be a negative Q delta V, right? So that means delta U is going to be less than 0. All right. U is going to be equal to positive Q times a negative delta V. And that means U is going to be negative. And so that means delta U is less than 0. And so will there be any work done? Well, if negative delta U is work, then negative, and I should put a delta in front of this. So what does that mean? Well, this means that work is going to be equal to a negative, and if delta U is negative Q delta V, well, that is going to be positive Q delta V. And so this work is now going to be positive in moving a positive charge from I to F. So I had to find a way to delete that, and the only way I knew how to delete those markups is to close out the document and then restart it. So again, the electric field is doing positive work in moving a positive charge from I to F. Okay? Now let's figure out how much work the electric field does in moving a positive charge from I to F, given that this is a negative Q. Well, what I'm going to do is I'm going to change this color to blue, because blue I associate with negative Q. So we have a negative Q causing this we're causing a voltage here and a voltage here. So that'll be a negative voltages. Again, this is a distance R, and we're going to call this a distance 2R. So the voltage at I is going to be equal to K times a negative Q all over R. And let me mark that up to be showing a negative Q. Make it show a little bit cleaner. Negative Q divided by R. Which is just going to be negative 1 KQ divided by R. Well, the voltage at F is going to be equal to negative 1/2 KQ divided by R. This is a negative Q causing the voltage here. It's a distance 2R away, so negative KQ divided by 2R is just negative 1/2 KQ over R. So this is an interesting problem in that if the final voltage is negative 1/2 KQ divided by R, and the initial voltage is negative 1 KQ divided by R, the final voltage is greater than the initial voltage, which is going to result in a negative, in a positive change in voltage. So the final voltage is negative 1/2. The initial voltage is negative 1. So negative 1 is less than negative 1/2, so that means V final is greater than V initial, which is going to result in a positive delta V. Well, since we have a positive Q that we're multiplying by this, that's going to end up being a positive delta U as well. And so what does that mean? Well, work is equal to negative, and our delta U is a positive delta U. So a negative times a positive delta U is going to end up being a negative, is going to end up being a negative work. Okay, so work is going to be less than 0. So what does that mean? Well, that means work done is going to be negative. All right? All right, let's try another one. Let's find out the work done in moving a charge from I to F. Okay. So we're going to put a positive charge right here. Oops, and I should use red for the positive charge. So we're going to take a positive charge, and we're going to go a little bit quicker in this problem. We have a positive charge right here that's going to be in a high voltage. So the initial voltage is going to be very large, and the final voltage is going to be small. So that means this is going to be a negative delta V. V final is less than V initial. So that means it's going to be a negative V final. And what that means is that our delta U is going to end up being negative. Negative delta U. And, well, work done. So delta U is less than 0. So our work done is going to be work equals negative times a negative delta U. And that means the electric field is going to do positive work in moving this charge from here to there. All right. Let's try it again. So that means work done is going to be greater than 0. So let's try the same problem now, but we're going to do the right-hand side. So the hinging point of this is that the voltage at I is going to be 0. And the voltage at F is going to also be 0. It's the halfway point in between these two things. And along this line, the voltage has got to be 0. The voltages to the right are going to be negative. The voltages to the left are going to be positive. It doesn't matter what region. So that means V final is going to be equal to V initial. And that means this is going to be 0. So delta U is going to be 0. And that means the work done in moving a charge from I to F is going to be 0. All right. Capacitor problems. I love capacitor problems because they're pretty easy. Just like the last problem, the voltage along this line is going to be 0, right? So the V voltage along the this line is going to be 0. So VI is going to be equal to VF, which is going to be equal to 0, which means that delta U, change this is going to be 0, so 0 times positive is going to be 0, and that means there's going to be no work done in moving a charge from I to F. Well, how about over here on the left-hand side? We're going to take a positive charge and put it here. So the voltage here is going to be a positive voltage. So VI is going to be a positive voltage. VF is going to be a negative voltage. Okay. So you have a negative V here for the final voltage, and you have a positive V for the initial voltage. And so that's going to end up, so delta V is going to be negative. All right, so V final is less than V initial. And so a positive Q times a negative delta V means that delta U is going to be negative. And what does that mean? Well, you have a negative delta U. Work is going to be equal to negative times our delta U, which is negative. and that's going to end up being positive. So it's going to do, the electric field is going to do positive work in moving a charge from I to F. All right. So there are some worksheet problems that you're going to do, some tutorial problems that you're going to do in this chapter, and hopefully this tutorial is going to help you out. What I want you to do is move on to the sapling homework. So 6.02 and 5.03 in 131 and 112. 131 and 112, again, you're going to do this problem, but this time it looks like the voltage homework problem, but this time you're talking about delta, you're talking about potential energies. Okay, so be careful. There's potential energies, not voltages. Okay, and you're going to be talking about what is a potential energy and gathering all these charges together. Okay, you have two positive charges in distance, and these guys are equidistant. So what is potential energy in taking these charges from an infinite distance and bringing them close together? Okay, and you're going to be doing the same thing here. All right, that is this activity.